Today's lesson is primarily going to be over integration by parts, which is another method for finding antiderivatives. But before we get there, we're going to review some of the integration methods that we've already talked about. So on example A, this is our standard power rule problem, or as we like to say, bump up and divide. So I'm going to rewrite this, first of all, as the integral of 3x squared plus 5x to the negative 4 plus 2 sine of x. And the reason I need to do that is so that I can use the power rule on this middle term here, 5 over x to the 4th. And so now if I bump up and divide, if I increase my exponent by 1 for 3x squared, that'll be 3x cubed, divided by 3 will be x cubed, minus 5 over 3x to the negative 3. And then the antiderivative of sine is negative cosine, so this last term will be negative 2 cosine of x. Let me erase my, whoops, a little bit of an over erase there, but I can fill in the blanks here. Negative 5x to the negative 3 minus 2 cosine x, and then plus c. And this would be a perfectly fine way to leave the answer, or you could take that middle term and put the x cubed back into the denominator if you want to. It really is kind of up to you and what the answer choices, if it's a multiple choice question, sort of look like. On example B, we have the integral from 1 to 2 of x squared times x cubed plus 1 squared dx. And since this is a function inside of a function, my first instinct is to think about a u substitution. So I'm going to say let u be equal to the inside function, which would be x cubed plus 1. And that means that du would be 3x squared dx. And a careful just look at this particular function, I see that I have x squared dx in the problem. The only thing I'm missing is the 3. So I'm going to fix that by doing a 1/3 du is equal to x squared dx. And on this particular problem, this is a definite integral with bounds, and so since I'm going to be changing to u, I'm going to also change my bounds to be in terms of u. So my u of 1 is going to be 1 cubed plus 1, which will be 2, so that would be my new lower bound. And my new upper bound, I'm going to plug in the original upper bound to my formula for u, and that's going to give me a new upper bound of 9. And so now when I go to rewrite this, this is going to become 1/3 of the integral. I'm going to put du down here at the end, from 2 to 9 of u squared. Okay, because this part right here, I'll highlight it in, try to highlight it in blue. Okay, that is my u squared piece. Okay, so now I'm ready to take the antiderivative of u squared. So this is going to be 1/3 times 1/3 of u cubed, evaluated from 2 to 9. And continuing to evaluate this by hand, I'm going to have 1/9 of 9 cubed minus 2 cubed, which will equal to 81 minus 8 over, let's see here, 8 over 9. And so this is going to end up being 721 divided by 9 as my final answer. So just as a reminder on u substitution, when you change to u, you need to go ahead and change your bounds and then never go back to x. Notice back up here on this line right here, I never went back to x. I just worked in u for the rest of the problem. Okay, the next question is a classic u substitution in your head, as I like to say. So I have the integral of e to the 3x dx, and so I know that the integral of e to the u du is just e to the u plus c. But in this particular case, I have an exponent in this problem of 3x. And so that means I'm going to need a constant in the front of my antiderivative in order to cancel out the derivative of that 3x, which would be 3. And so this is going to end up being e to the u like we would expect it to be, plus c, but in the front I've got to have something that would cancel the derivative of that exponent, which in this case will be a 1/3. And so we've kind of been talking about this idea for a while of u sub in your head without having to write down u equals 3x, du equals 3dx, and then, rearranging the integral to be in terms of u. Because if we need to do that today when we talk about integration by parts, then the problem is going to have a lot of different variables flying all over the place, and it's going to be very confusing. So it's way easier if we can do a problem like this in our head. Okay, example D is also a u substitution problem in your head, and since this is a definite integral, your question might be, do I need to change the bounds here? And my answer to that is I'm not going to change the bounds because I'm going to stay in the variable x since I'm going to be doing this u substitution in my head. So my antiderivative of sine 3x will be negative 1/3 cosine of 3x. And since I'm staying in x, I'm going to stick with my original bounds, 0 and pi over 6. Okay, so now continuing to use the fundamental theorem of calculus, I'm going to have negative 1/3 cosine. If I plug in my upper bound, pi over 6, that's going to be 3 pi over 6, or pi over 2. And then minus negative 1/3, so that becomes positive 1/3 cosine of 0. And since cosine of pi over 2 is 0, that means this term will go away. Cosine of 0 is 1, and so therefore our final answer here will just be 1/3. Okay, example E is also a u substitution in your head, and before you start thinking that this might be like 1/3 secant cubed of 5x or something like that, remember that we have an antiderivative rule for secant squared of u, and that would be our tangent. So this is going to be tangent of 5x, but because that inside function has a derivative of 5, I left a little bit of space here to put my 1/5, and then I'm going to evaluate that from 0 to pi over 20. And again, since I'm not changing to the variable u, I'm going to keep my bounds the same. Okay, continuing here with the fundamental theorem of calculus, this will say 1/5 tangent of 5 pi over 20, which is going to reduce to pi over 4, minus 1/5 tangent of 0. And since tangent of 0 is 0, that term will go away. Tangent of pi over 4 is equal to 1, so the answer here to this integral will be 1/5. Okay, and then letter F, one more u sub in your head problem, and it might be helpful to rewrite this as the integral of 1 minus 3x to the negative 1 power. When you rewrite it like that, it should become obvious what rule this is going to be, that this is going to be natural log of the absolute value of 1 minus 3x. Don't forget plus c in this case, since this is an indefinite integral. And then finally, the inside function, this inside part right here, has a derivative of negative 3. And so because it has a derivative of negative 3, I need a negative 1/3 in the front of that natural log. That way, if I were to take the derivative of my answer, we would end up with what we started with, which didn't have a negative 3 in the problem. Okay, so I hope that's making sense. I'm really trying to drive home this idea of a u substitution problem in your head, so to speak, whenever the derivative of the inside function is a constant. If it's a constant, then we can deal with that just by putting the reciprocal of that derivative in the front of our antiderivative. Okay, and then one last review question here. We have the integral of 4x over x squared plus 9 dx. And you can remember in our last lesson, we had 3 different integrals to kind of talk about at the end of the lesson last time. We had this integral, 4 over x squared plus 9, and then I gave you 4x over x squared plus 9 dx, and then finally 4x squared over x squared plus 9. And we kind of talked about the differences in these 3 problems. And what we kind of came away with is that if there was no x in the numerator, like this first example, that was going to be an inverse trig problem because it fits the arctangent rule whenever there's not an x in that numerator. In the second problem, which turns out to be just like our example G here, we notice that if we were to take the denominator to be our u, that our du would be in the numerator except for the wrong constant. And we can fix the wrong constant being there. And then in the last example, so just as a backup, this would be a u sub problem. And then our third example, because this is a rational function where the degree is the same on the top and the bottom, this would actually be a long division problem. Okay, so you can refer to your notes from last time about what we did to solve those three integrals. And so this example G would fit the middle of those three categories. And so I'm going to let u equal to x squared plus 9 here. That would make my du equal to 2x dx. And if you notice, we have x dx in this problem. What we do not have is a 4. And so what most people said in class is that we want to just multiply this equation by 2 on both sides so that we have our 4x dx, and we can replace that with a 2 du. Okay, so I'm going to go ahead and do that. And so this integral is going to become 2 integral of du. And then if you look back up here in the original problem, the part that I do not have circled would be 1 over u, or another way to say that is u to the minus 1. And so when I take the antiderivative of u to the minus 1, that's going to become the natural log of the absolute value of u plus c. And since this is an indefinite integral, I'm going to go ahead and go back to x and write this as 2 natural log of the absolute value of x squared plus 9 plus c. Okay, so now that we've kind of reviewed some of the integration methods that we've already talked about, let's move on to our new integration method for today, which is called integration by parts. And integration by parts is going to be used in order to find the antiderivative of a product. So this is a way to find the antiderivative of a product of two functions, and in most cases the two functions that we're talking about are going to be different types of functions. So maybe like a polynomial times a trig function, or a polynomial times an exponential function, or maybe an exponential times a trig. And so those are kind of the things that you're looking for when to use integration by parts, is whenever you have the product of two different kinds of functions. And so I'm just going to take a second here to sort of derive the formula for integration by parts, and it comes from the product rule of derivatives. So if I start here with the derivative with respect to x of uv, I know that that's going to be uv prime plus vu prime, just using the notation that I have there, u times v. Now, if I integrate both sides of that, then on the left side, the integral of the derivative just sort of cancels out. So that's why I have uv here. And that's going to equal to, I'm going to use a little bit different notation here. I'm going to say the integral of u dv, so that dv is taking the place of v prime, plus the integral of v du. And if I rearrange this formula now, I'm going to get the formula for integration by parts, which is a formula that you should memorize. So the integral of u dv is going to equal to u times v minus the integral of v du. And that's the formula that I'm going to copy here into our box. So the integral of u dv is equal to uv minus the integral of v times du. And this is a formula that you should memorize. One of the most challenging parts of integration by parts is going to be choosing a u. And so we're going to talk about a way to do that. The way that I was taught and the way that I've always done it is using this acronym, which is sometimes just said as LIPIT. And so this LIPIT is a way to choose your u. So a way to choose your u. And so this is just an acronym that stands for different types of functions. So the L stands for a log function. I stands for inverse trig. P stands for polynomial, so I'm just going to write poly, and so that would be like your, x to some power. E stands for exponential. And T stands for a trig function. And so basically what this means, and the order definitely matters here, is that let's say that you have a logarithm in your integrand. Well, then I'm definitely going to choose that for u because L comes first in this acronym. If I have an inverse trig and I don't have a logarithm, I'm going to choose inverse trig. If I have a polynomial and a trig function, then I'm going to choose polynomial because p comes before t. If I have an inverse trig and a poly, then I'm going to choose the inverse trig because inverse trig comes before polynomial in this acronym. So I hope that's making sense for you. We'll kind of reiterate that as we go through the examples. Okay, so we're going to start with our first example here. We have the integral of x times sine x dx. And so since I noticed this is the product of two different kinds of functions, my first thought is to use integration by parts. So for integration by parts, I know that I'm going to try to pick a u, and so using my acronym, LIPIT, I notice that this is a product of a polynomial and a trig, and since polynomial comes before trig, I'm going to let my u be equal to x. That means that my dv is going to be everything else in this problem. So I'm going to make my dv sine x dx. So remember, the formula is the integral of u dv is equal to uv minus the integral of v du. And so you can kind of see here, this is my u and this is my dv part right here. Okay, so now calculating my du, that's just the derivative of x, which is just 1 dx, and then v is going to be the antiderivative of sine x, and the antiderivative of sine x will be negative cosine x. Okay, so now that I have those things ready, I'm going to go ahead and use the formula. So this says that this will be uv, so u times v will be negative x cosine x, minus the integral of v, negative cosine x, times du, which is dx. Okay, so now my focus is going to be on that new integral at the end of this. I'm going to go ahead and take the opportunity to show you that this negative right here and this negative right here will become a positive, so this will be plus the integral of cosine x dx. And so this is now, as my final answer, I know what the integral of cosine x is. It's sine x, so I'll replace the integral of cosine x with sine x, and then don't forget about my plus c. Okay, so I chose my u. That means everything else was dv. Find the derivative of u to get your du. Find v by taking the antiderivative of your dv, and then just use the formula, and that's pretty much the whole story there. Now, sometimes you have to repeat the process, which means you have to use integration by parts more than once in the same problem. And so I notice here that this is the integral of x squared e to the x dx. And so using my acronym LIPIT, I notice that this is the product of a polynomial and an exponential function. And since polynomial comes before exponential, I'm going to let my u be equal to x squared, and my dv is going to be e to the x dx. Okay, that means that my du is 2x dx, that's the derivative of x squared, and v is the antiderivative of e to the x, which is just itself, e to the x. Okay, so this integral will equal to u times v, so that's x squared e to the x, minus the integral of v du. So that would be writing it in sort of an order that makes sense, 2x e to the x dx. And so now my focus is going to be on this integral. And so looking at that integral, I notice it's the product of two different kinds of functions, one of them a polynomial, one of them an exponential. And so I'm going to use by parts again on this highlighted integral. And so again, using LIPIT, I know that u is going to be equal to 2x. That means that my du is going to be 2 dx, and my dv is going to be everything else other than the 2x, which is e to the x dx. That means that my v is the antiderivative of that, which will be e to the x. Now this term, when I go to the next step, is just going to carry down. So this will be x squared e to the x minus... Now, when I do this next by parts, I'm going to open a parentheses because the minus that is right here is going to have to go to both of those terms. Oh, excuse me. Okay, so I'm going to do u times v, which is 2x e to the x, minus the integral of v du. And writing in that in an order that makes sense, that would be the integral of 2 e to the x dx. I'm going to spend a step here just to distribute my negative sign. So x squared e to the x minus 2x e to the x, and then minus the negative is going to become plus the integral of 2 e to the x dx. And so now my final focus in this problem is going to be on the integral that's right here. And I know the antiderivative of 2e to the x. That one is easy and doesn't require integration by parts or u substitution or anything like that. And so now I'm ready to write my answer. X squared e to the x minus 2x e to the x plus the antiderivative of 2e to the x, which is just itself, and then don't forget plus c. Okay, so on those repeated problems, you're going to have to use integration by parts more than once. Now, if you thought the last problem was a lot of work, then you're in luck, because there is a faster way to do that problem, and we're going to use this approach any opportunity that we get just because of how fast it really is. So this is called the tabular approach to integration by parts. The only bad news about the tabular approach is it can only be used in two certain situations. Whenever you have a polynomial multiplied by a trig, which would be like example 1, or a polynomial times an exponential, which is like example 2. So we're actually going to redo example 2 using this tabular approach. Now the first step is still the same. You have to choose a u and a dv. And since polynomial comes before exponential, I'm going to choose my u to be x squared. But I'm going to write it in a little bit of a different format. I'm going to have a u column, and I'm going to have a dv column. Okay, so x squared is going to be my u, and my dv is going to be e to the x. Now for my u column, what I'm going to do is I'm going to take the derivative all the way down this list until I get to 0. So I'm going to take the derivative until I get to 0. Okay, so the derivative of x squared will be 2x. The derivative of 2x will be 2. And the derivative of 2 will be 0. And so I've satisfied what I wanted to do. I took the derivative of my u until I got down to 0. For my dv column, what I'm going to do is I'm going to integrate until I finish the list. So integrate until I get to the end of the list. And so if I start taking the integral of e to the x, that's a pretty easy example to work because the integral of e to the x is just itself. Okay, once I do that, the signs of these things are going to alternate. So I'm going to put a plus sign here, a minus sign here, plus sign, minus sign. So it starts with plus and then alternates. And to get our answer, we're just going to multiply diagonally these terms. So x squared times e to the x, that's going to be my first term in my answer, x squared e to the x. My second term is going to be negative 2x times e to the x. The negative came from the negative that was right here in my alternating signs. Okay, so negative 2x e to the x. Whoops, let me do that in my black color. Negative 2x e to the x. And then my last term in my answer is going to be positive 2 times e to the x. And so if you'll notice, you can go back and look at your notes if you want to, this is the exact same answer that we got by doing repeated integration by parts. It was just much faster this time using the tabular approach. But I do want to remind you, you can only use this tabular approach if it's a polynomial times a trig or a polynomial times an exponential. Okay, on the next example problem, we aren't going to be able to use the tabular approach, so we're going to have to go back to our approach that we used on the first two examples, since we have a polynomial times a logarithm. So if we remember our acronym, LIPIT, then since logarithm comes before polynomial, we're going to choose our u to be that logarithm, natural log of x, and dv is going to be everything else. So that would be x squared dx. Okay, I'm going to go ahead and calculate what my du is. So that would be the derivative of natural log of x, which would be 1 over x dx. And my v is going to be the antiderivative of x squared, which is just your standard bump up and divide, 1/3 x cubed. Okay, so my formula says u times v, so I'm going to write that in an order that makes sense, 1/3 x cubed, natural log of x, minus the integral of v du. So that would be 1/3 x cubed multiplied by 1 over x dx. Okay, well, I can go ahead and simplify that a little bit and clean it up. I'm going to go ahead and move the 1/3 as a constant in front of the integral sign, and then x cubed times 1 over x is just x squared. Okay, and so now my focus, as it has been on the previous problems, is going to be on this integral right here and finding its antiderivative. And that's just a simple bump up and divide problem. So 1/3 x cubed natural log of x will just float down. And then this will be minus 1/3 times the antiderivative of x squared, which is 1/3 x cubed plus c. And to make my final answer look a little bit nicer, I'm going to go ahead and multiply together those two 1/3. So minus 1/9 x cubed plus c. Now, everything we've done so far has been an indefinite integral, so let me just show you real quick what would happen if you have a definite integral with bounds or limits of integration. And this is an integral of x sine x. So that is a product of a polynomial and a trig. That means I'm going to be able to use the tabular method here. And so if I make my choice for u and think about my acronym, polynomial comes before trig, so my u is going to be x. And so my dv is going to be sine x. So if I take my derivative of u until I get to 0, the derivative of x is 1, the derivative of 1 is 0, and then take the antiderivative of dv, so the antiderivative of sine x would be negative cosine x, and the antiderivative of negative cosine x would be negative sine x. Okay, do not forget that these signs are supposed to alternate, so positive, positive, and then we're going to multiply diagonally. So x times negative cosine x, and then -1 times negative sine x, and that will be our antiderivative. So I'm going to have negative x cosine x minus negative sine x is going to become plus sine x, and that's going to be evaluated from 0 to pi over 2. Okay, so if I plug in pi over 2, that'll say negative pi over 2 times cosine of pi over 2 plus the sine of pi over 2. So there's my evaluation at the upper bound minus my evaluation at the lower bound. So that will be -0 cosine of 0 plus the sine of 0. Okay, and there's only going to be one term that survives here. Cosine of pi over 2 is 0, so that will go away. 0 times anything is 0, so that will go away. And sine of 0 is 0, and so the only thing that's left here is sine of pi over 2, which would equal to 1. Okay, this next problem is going to take us a little bit of time. I noticed that it's the integral of an exponential and a trig. So thinking about my limit, I know that the exponential comes first, and so that means that my u is going to equal to e to the x. That means that my dv is going to be cosine of 2x, and so I can calculate what my du is, e to the x dx, and my v, which is going to be the antiderivative of cosine of 2x, and so this is kind of the first place where that u sub in your head really makes a big difference. So the antiderivative of cosine 2x, of course, would be sine 2x, but don't forget about the 1/2 that needs to go in the front because of the u sub in your head part. Okay, so if I do u times v, then this is going to be 1/2 e to the x sine of 2x, so I'm going to write that in an order that makes sense, minus the integral of v du, which will be 1/2 e to the x sine of 2x dx. Okay, so now my focus is going to be on this integral, and I notice that again it is the product of an exponential and a trig, and so I'm going to need to use integration by parts once again. So I'm going to allow u to be my exponential part, 1/2 e to the x, and my dv to be my sine of 2x. That means that my du is the derivative of 1/2 e to the x, which is just itself, and my v is going to be the antiderivative of sine 2x, which will be negative 1/2 cosine of 2x. Okay, so now this term right here is just going to float down, and we're going to have 1/2 e to the x sine of 2x minus, when I do this part of the integration by parts, that minus is going to have to go to both terms, so I'm going to go ahead and open a parentheses, and this is going to say negative 1/4, okay, e to the x cosine 2x. Okay, so just in case you're not sure where the 1/4 came from, I multiplied u times v. This had a 1/2, this had a negative 1/2. So when I multiplied those together, I got negative 1/4. Okay, minus the integral of v times du. So that will be also minus 1/4 e to the x cosine of 2x dx. Now, I'm going to take a couple of preliminary steps here, and I'm going to point a couple of things out. First of all, I have a negative sign right here and a negative sign right here, and so what that's going to allow me to do is change this to plus plus. So I'll do that with a different color so that you can kind of see what's going on that part. And then I'm going to go ahead and distribute this negative sign into that big parenthesis. So I'm just taking a step here to kind of clean everything up. And so this is going to say 1/2, oops, let me do that in my black color, 1/2 e to the x sine of 2x plus 1/4 e to the x cosine of 2x, and then minus the integral of 1/4 e to the x cosine of 2x dx. And so now our focus is going to be on this integral right here. And you might notice that it's again an exponential times a trig. So if you're thinking like I'm thinking right now, it looks like we're just kind of going in circles. But the good news, and this is kind of the approach anytime that you have an exponential times a trig, is that that highlighted integral right there down at the bottom in yellow is the same as my original integral. And so what I'm going to do here is I'm going to call the original integral some variable name. So I'm just going to be real clever here and call that integral capital I. And so this whole time we've been doing I is equal to, I is equal to, I is equal to. And now this highlighted thing that I have down here at the bottom is going to be 1/4 of I. And so what I have here is I is equal to this 1/2 e to the x sine 2x plus 1/4. This was a 4, by the way, if that wasn't clear. E to the x cosine of 2x minus 1/4 of I. And my objective is to solve for I. So I'm going to add 1/4 I on both sides. And that's going to give me 5/4 I is equal to 1/2 e to the x, sorry, let me erase and try that again. 1/2 e to the x sine of 2x plus 1/4 e to the x cosine of 2x. And to get I by itself, I'm going to multiply this entire equation by the reciprocal of 5/4, which would be 4/5, and that's going to give me my final answer. So I'm going to get that this integral is equal to 5/4 times, 1/2 times 4/5 is 2/5. So 2/5 e to the x sine of 2x. And then 1/4 times 4/5 is going to be 1/5. So this will be plus 1/5 e to the x cosine of 2x. And so there is my final answer. Now, I mentioned this in class. This is a problem that takes quite a while to do, and so because of that, you're more than likely not going to encounter something like this on the AP exam. But I know that several of you are going to be engineers or do something related to mathematics, and so you're going to need to know how to do an integral like this. Your college professors will expect you to be able to do a problem like this, and so that's why I put it into the notes and also give you a problem like it on your assignment. Okay, in our next example, we're going to look at a problem that is more similar to what you might find on the AP exam because it has a table in it. And it's not going to look like an integration by parts problem, at least any that we've talked about before, because I'm not going to be able to use Lipit to figure out how to solve it. So basically, if you look at this integral, the integral from 0 to 1 of x f double prime of x, what I notice is that that is a product of two different kinds of functions, x and f double prime of x, and I don't really know a lot about f double prime of x other than what they tell me in the table. And so since it's a product, I'm thinking that it could possibly be an integration by parts problem. So I'm going to choose a u and a dv based on what I have in the question. And so we kind of had the discussion, should u be x or should u be f double prime of x? And so the first thing that we just kind of did was we said, okay, well, what if u was f double prime of x? In that case, du would have to be f triple prime of x. And because I don't know anything about f triple prime of x, this seems like a bad choice for my u. So I'm going to kind of cross that out a little bit and see if I can try to make u be x, and if I can have that fit the problem. So if u is x, that means that dv is going to be f double prime of x, dx, which means that my du will be equal to dx, and my v will be the antiderivative of f double prime, which would just be f prime of x. And notice that I have something in this problem about f prime of x in my table. So this seems like a good choice and a good way to approach this particular problem. So using my formula for integration by parts, this is going to be u times v, x f prime of x, evaluated from 0 to 1, minus the integral of v du. So that's going to be f prime of x dx from 0 to 1. Okay, so for this first term, x f prime of x evaluated from 0 to 1, I'm just going to use the fundamental theorem of calculus. So that will be 1 times f prime of 1 minus 0 times f prime of 0. For the second term, I know the antiderivative of f prime is f. And so to evaluate this second integral, the one I'm talking about is the one right here, I'm going to use the fundamental theorem of calculus. So I need an antiderivative of f prime. I know that that is f of x. And I'm going to evaluate that from 0 to 1. And so this is going to end up being, I'm going to go ahead and plug in some numbers here. So f prime of 1 from the table is 6, times 1 is obviously just 1, minus this term right here has a 0 in it, so I know that that's just going to go away. And then minus f of 1 minus f of 0, using the fundamental theorem of calculus. So f of 1 subtract f of 0, and then just continuing going with the evaluation here, 6 minus f of 1 is 2, minus f of 0 is 1, and so what I end up getting here is 6 minus 1, which would be equal to 5. Okay, on the next question, we have the integral from 1 to 4 of f of x dx is equal to 51. We want to use that information in the table to find the integral from 1 to 4 of x times f prime of x dx. And so once again, I'm not going to be able to use Lipit, but I do recognize that this is the product of two functions, x and f prime of x. So if I let u be equal to x, similar to the previous example, that means that my du is going to be dx. And my dv is going to be everything left over in this problem, which is f prime of x dx, which means that v is going to be the antiderivative of f prime, which would be f of x. Okay, so using my formula for integration by parts, I know that I'm going to have x, f of x, u times v, evaluated from 1 to 4 minus the integral from 1 to 4 of v du. So that would be f of x and dx. Okay, so continuing here with the fundamental theorem of calculus, plugging 4 into x f of x, that's going to be 4 times f of 4 minus 1 times f of 1. So I'm going to erase this and put that 1 times f of 1. And then for this integral here at the end, okay, I was given the value of that in the problem. The problem told me that that integral was equal to 51. So I'm going to put in here minus 51. Okay, so this will be 4 times f of 4, which I'll get from the table. That's equal to 41. Minus 1 times f of 1. F of 1 is 2. And minus 51 is going to give me a total of 111. Okay, the last two examples don't look like integration by parts, at least as far as we've talked about it so far. They're not products of two different kinds of functions, but they are lone, either a logarithm or a lone inverse trig function. And so whenever that's the case, we can use integration by parts as one of the methods for finding the antiderivative. So I'm going to let u here be equal to the natural log of x squared plus 4. And so dv has to be everything else. Well, the only thing left is dx. And so I'm going to let my dv be equal to dx. That means my v is going to equal to just x. That's the antiderivative of 1, if you want to think about it like that. And my du will be the derivative of the natural log of x squared plus 4. Remember that the rule is u prime over u, and so that would be 2x over x squared plus 4. Okay, so using my formula for integration by parts, this integral is now going to become u times v, so x times the natural log of x squared plus 4, minus the integral of v du, and when I multiply x by 2x over x squared plus 4, I'm going to get 2x squared over x squared plus 4 dx. Okay, my focus now is on this integral, 2x squared over x squared plus 4. And notice that this fits the category where the numerator and denominator have the same degree. And so therefore, I'm going to use long division to find the answer. So I'm going to come over here, and in red, I'll do my long division. X squared plus 4 will go on the outside, since it's the denominator. 2x squared will go inside. I'm going to divide 2x squared by x squared, and so that's going to give me 2. And then multiply 2 times x squared plus 4, so that will be 2x squared plus 4. And then subtract, and I'll do that in a different color here, so minus. And when I do that, my remainder ends up negative 4. And so this integral right here will now become, I'll just go ahead and write the entire line, x ln of x squared plus 4 minus the integral of my quotient, which is 2, that was what was on top right here, minus 4 over x squared plus 4 dx. Okay, so continuing going here, this x natural log of x squared plus 4 will just float down, minus the antiderivative of 2, so that's just going to be minus 2x, and then minus negative, so minus a negative is going to become positive, so I'll go ahead and write a plus sign here, the antiderivative of 4 over x squared plus 4, and that fits my arctangent rule. So I'm going to write down my 4, since that's just a constant. It's going to sort of hang out in the front. And for this arctangent integral, I'll do that in yellow. I know that my a is going to be 2, since my constant of a 4 right there. My u is going to be x, which means that my du is going to be dx. And so I know that the antiderivative of that is going to be 1 over a inverse tangent of u over a. And so I'm just going to import that into my last line answer here. So times 1/2 arctangent, running a little bit out of space, but that's okay. And then don't forget about plus c. And so my final answer, I can write x natural log of x squared plus 4 minus 2x plus 4 times 1/2 gives me 2 tangent inverse of x over 2 plus c. So I like that problem because it introduces a lot of these different integration methods that we've already been talking about. Again, that's probably not something that you'll be asked to do on the AP exam only because of time constraints, but it's a really good problem for you to know how to do because, like I said, it will test a lot of different things that we've already learned. Okay, so this example is similar to the last one. It's just an arctangent function sort of by itself. And so whenever you see that going on, then you need to think integration by parts. So again, there's not much here to choose for u, so I'm just going to let my u be equal to arctangent of 3x. And the only thing left there to choose for my dv would be dx, which means that my v is going to be the antiderivative of that, which would just be x. And my du will be the derivative of arctangent of 3x, which would be 3 over 1 plus 9x squared. Okay, so remember the rule for arctangent would be the derivative of u, which would be 3x, so that would be 3, over 1 plus u squared, so 9x squared. Okay, so using our formula for integration by parts, I'm going to have x arctangent of 3x minus the integral of v du, and so that would be 3x over 1 plus 9x squared. And so now this integral right here fits into our logarithm category because we have that x in the numerator and it's 1 degree less than the degree of the denominator. And so what I could do, and I'll do this in yellow, is I could choose my u to be 1 plus 9x squared, and that means my du is going to be 18x dx. Let me fix that there, 18x dx. And I have that in the numerator, except I don't have an 18, I have a 3. And so to get my 3, I'm going to divide both sides of this by 6. And so that would give me 1/6 of du is going to equal to 3x dx. Okay, so now I'm sort of able to, I'm going to continue this side work over here in my yellow. I'm going to replace that integral up there with 1/6 the integral of du, and so that's going to replace my 3x dx part, and then what's left is u to the minus 1, and so this is going to fit the logarithm rule. Okay, so I'm ready to go back to black now and continue writing the answer here, which is x arctangent of 3x minus 1 over 6, the natural log of the absolute value of 1 plus 9x squared, and then plus c. Okay, so there's one more bonus problem that I want to work for you because you're going to need this integral in your notes, and we haven't talked about how to find this antiderivative yet, and so I just wanted to make sure that you had this for your homework assignment because there's going to be one problem where you need this antiderivative. So for integral of tangent x dx, the object here is to rewrite this using a trig identity. And so I remember from pre-calculus that tangent x is the same thing as sine x over cosine x. And now that it's in this form, I can use a u substitution. So I'm going to let u be the denominator, cosine of x. That means that du is negative sine x dx. And I notice that I have that in the problem except for the negative sign. So I'm going to make this negative du is equal to sine x dx, and so what that means is that I can replace that circled part in red with negative du, and what's left is cosine of x in the denominator, and so that's going to be my u to the minus 1. So this again will fit the logarithm rule, and it'll be negative natural log of the absolute value of u, which is cosine x, and then plus c. Okay, so when you get to the problem on your homework, that's the integral of x times secant squared x. You're going to eventually need the antiderivative of tangent x, and now you should know how to do it. If you guys have any questions on integration by parts, then please feel free to let me know, and I'll talk to you guys next time.